This is the second topic in the completing the model of the atom unit. You can see the title of the unit is the atomic emission spectra and the Bohr hydrogen atom. Our learning targets for this video, we want to be able to explain how atomic emission spectra are produced. We also want to be able to rank the photon emissions and absorptions in the Bohr atom by wavelength, frequency, and energy. So to start with, we'll just be talking about this first learning target, being able to explain how atomic emission spectra are produced. So atomic emission spectra, a little background first. In order to understand what atomic emission spectra are, we want to understand what white light is. White light is simply the term that we use for whenever we have all frequencies of visible light. This is what it would look like. You've seen this, so in class we went outside, we looked at the spectrum given from the sun, and it should have looked very similar to this. Notice we have all colors of visible light ranging from the longest wavelengths, the red end, to the shortest wavelengths, the violet end. Just a little FYI here, the scale on this, the numbers you can see here, for example, 7,000, 6,500, 6,000, those are in angstroms. 1 angstrom is 1/10,000,000th of a meter, so it's actually 10 times smaller than a nanometer. So 7,000 angstroms would be 700 nanometers, just so you guys know what you're looking at there. And notice it is a continuous spectrum. Realize that there are no breaks in this. There are no breaks in the spectrum. We get absolutely every wavelength or frequency of visible light in white light. We can separate it by a prism. This is exactly what we did with the spectroscopes. You went outside, you pointed the spectroscope to the sky, to sunlight, and then as that light comes in into the diffraction grating of the spectroscope, or in this case a prism, it gets separated into its component wavelengths. You can see we get the colors of the rainbow there, the red, orange, yellow, green, blue, indigo, violet. Here's another depiction of the same thing, more of a graphic of what you see here. You can see the red end always gets bent the least amount, and the violet end always gets bent the most from that dispersion from the prism. So what exactly are atomic emission spectra, and how does that apply to what we're trying to figure out here? Well, the problem was this, is that the models of the atom back in the early 1900s, they predicted that white light should be emitted from atoms upon their release of energy. In other words, we should see what we see from the sun. But that is absolutely not what we see. Just as an example, let's take a look at the hydrogen emission spectrum. We've already looked at this in class, and we'll look at it in class again now that you've seen this video so you can get a better understanding of what we're talking about here. But if we have a gas discharge tube containing hydrogen, that's what we have here, so this is what you guys have seen in class, and we run it through some sort of prism or diffraction grating, that we only get 4 colors of light. You can see here it's being separated into its 4 colors, and here at the bottom is a schematic of what we get. We get a red, kind of a blue-green, a blue-violet, or a violet, and then a violet. And this last one here, the one with the shortest wavelength, it's actually really hard to see if you're just looking with your naked eye because it's approaching the ultraviolet. So you may or may not have seen that one whenever you were looking at this spectrum in class. Here's another picture of the same thing. We have a hydrogen emission tube here. That's what you guys are familiar with. You've seen that in class. And then we get these 4 colors, the red, the greenish blue, and here are the 2 violets. Again, this one here at the very end, it's pretty faint, so it's kind of hard to see. So you may or may not have seen that one in class. Here are some other emission spectra. Here's helium, and you can see it's very different than hydrogens. And most of these we've already looked at in class, at least a little bit. I'm just going to show you several of these here. Here is mercury. You can see there's even more lines in mercury's spectrum, and varying from the violet end all the way to the red end. Here's neon. Notice neon happens to glow red. That's why neon lights are called neon lights, as the first ones contain neon. And the reason why it looks red is there's all sorts of red wavelengths or frequencies being emitted. You can see that here in the emission spectrum. So here's just a graphic comparing three different emission spectra, that for hydrogen, mercury, and neon. You can see how different they are. And you can see that they're obviously not the same. So this is a problem for scientists. We had to have a way of understanding why they were so different and why we only got certain wavelengths or frequencies of light. Well, to review what it is that we've seen here, we can see that each atom emits a specific set of frequencies of light that it's emitted by atoms of an element. This is what an atomic emission spectrum is. The problems with this, we've already said them, we'll summarize them here, is that there's no model of the atom that would account for this, and that they're different for every element. So that's a problem. Well, the first solution to the problem came in the form of what is now known as the Bohr hydrogen atom. It was proposed by a Danish physicist by the name of Niels Bohr. You can see he proposed this in 1913, so a little over 100 years ago. And his solution was that the hydrogen atom has quantized energy levels. Now, this is not the first time we've seen this term quantized or quantum. We'll explain what that means here in relation to this atom here in just a second. What that tells us is that the electron has only certain allowable energies. In other words, the atom or the electron that makes up the hydrogen atom cannot have any random energy. It's only limited to certain values. So one way to depict that, and this is a drawing that you may be somewhat familiar with, maybe not this exact drawing, but oftentimes energy levels are depicted this way. Here in the middle, the dark black circle, that represents the nucleus of the hydrogen atom, and then each of the rings going around it represent a different allowable orbit or energy level of the electron. And you can see here the energy levels are labeled with orbits. There's orbit in 1, 2, 3, 4, 5, and it gives you the distance from the nucleus. Each of these different orbits, the electron would have a different amount of energy. And according to Bohr, the electron could only have these amounts of energy, or can only orbit at these distances. In other words, the electron was not allowed to orbit anywhere between any of these energy levels. It's very much like a ladder. If you're going to use a ladder, you're only allowed to stand on the rungs. You can't stand in between the rungs. Obviously, if you tried to, it might not work out very well for you. Same thing here. The electron is only allowed to have certain amounts of energy that correspond to these energy levels. Some terms associated with this we want to be familiar with. The ground state for any atom is simply the lowest possible energy state, or lowest possible energy level. For hydrogen, that would be when the electron was in the first energy level, the one closest to the nucleus here, towards the nucleus. The atom could also absorb energy to reach an excited state. An excited state would be any other energy level above the ground state. So for hydrogen, that would be when the electron was at n is equal to 2, 3, 4, 5, or so on. Now this particular schematic only shows the first 5 energy levels. There would be more though. And each of these energy levels is assigned what is called a principal quantum number, which we use the letter designation N. And this principal quantum number is assigned values of 1, 2, 3, etc. So 4, 5, 6 going on for each energy level. Whereas N increases, then the amount of energy associated with that level also increases. So let's use this idea of the Bohr hydrogen atom and quantize energy levels to explain how the hydrogen emission spectrum, or any emission spectrum for that matter, gets produced. So what we're seeing here is, on the right here, is just a diagram of the first 3 energy levels of hydrogen. Now one thing I'd like to point out here, and this is a theme we'll keep coming back to, notice how the energy levels are not equally spaced. That is intentional. This is one thing that Bohr showed in his calculations, that as we went up in energy level, each energy level got closer to the next level than it was to the previous one. So the spacing continues to get tighter each time on the way up. So the atom, you can see here, it starts in the ground state. This red dot here that the laser pointer is next to represents the electron. It starts in the ground state where the electron is at energy level 1. Well, the atom absorbs energy. When that happens, the electron will no longer be in the ground state. it becomes excited. So in this case, the diagram is showing it go from n is equal to 1 up to the n is equal to 3 level. It could have gone to 2, it could have gone to 4, it could have gone to 5. It just depends on how much energy was absorbed. So now the electron is in an excited state. In other words, it's no longer in the first energy level. N is greater than 1 at this point. The electron in the atom is not going to stay in this excited state forever. It's going to fall back down to a lower energy state at some point. However, not necessarily back to n is equal to 1. It could come back to the ground state or the first level. It doesn't have to, though. In this case, the diagram is showing the electron going from the third level down to the second level. Now when that happens, energy has to be emitted because now the atom has less energy. The second energy level has less energy than the third. So the atom had to lose whatever amount of energy is the difference between n is equal to 3 and n is equal to 2. And it does that in the form of a photon. We can see here the phrase just says that it releases a photon, and that's what this squiggly line here is for, to show that a photon is being given off. And likewise, if it goes through another transition, or in this case it's going from n is equal to 2 to n is equal to 1, it's going to give off another photon. And here's the key idea to understanding all this about the atomic emission spectrum. The energy of the photon that's released has to be equal to the energy gap between the levels. So if we look at our diagram here, this second photon that we showed getting released here, where the atom went from n is equal to 2 down to n is equal to 1, the energy of this photon that's being given off, the energy of that photon is equal to whatever the difference is between these two energy levels. Likewise, the energy of the photon given off here when the atom went from n is equal to 3 to n is equal to 2, that is also equal to this gap in energy between these two levels. To summarize that, here is an equation. We can see that the energy of the photon is equal to delta E, where delta is just the difference in the energy. So that would be the final energy of the atom minus the initial energy, which is still equal to h nu. That's the equation that Einstein was able to show from his understanding of the photoelectric effect. So we can say for each of these electrons that their energy is equal to Planck's constant times their frequency. Now obviously their frequencies are different because we have different amounts of energies, but that's just because these energy level gaps are not the same. So to summarize all of this, if you're going to remember one thing from this video, it would be the statement we have here at the bottom now. It simply says the atomic emission spectra are discontinuous due to the presence of quantized energy levels in atoms. In other words, these photons that are being emitted cannot have any energy, any random amount of energy. They can only have a certain amount because the gaps in the energy are quantized, because the energy levels that make up atoms are quantized as well. Atoms cannot have any random amount of energy. Here is another picture of the Bohr hydrogen atom. I like this one for a couple reasons. First of all, notice something we mentioned earlier. As we go up in energy level, here the bottom is n is equal to 1, then we go up to n is equal to 2, 3, 4, etc., that each of these energy levels is getting closer together. And that is absolutely the case. The higher up we go, the closer and closer the energy levels get. Another reason I like this is it's specifically showing which transitions or which changes in energy level give us the visible light. We can notice here in the middle there is a series of transitions labeled the Balmer series, and it says from En, meaning any energy level n, down to the energy level equal to 2. So for example, 3 to 2, 4 to 2, 5 to 2, 6 to 2. These are the ones that give us the visible transitions. So notice the red wavelength that we get when we go from n is equal to 3 to n is equal to 2. That's the transition that occurs when we get the red light, or that red photon. The 4 to 2, that's the green one, or might call it turquoise, that greenish blue. The 5 to 2, that's the blue, or kind of the bluish purple. And then the 6 to 2, that is the violet or the purple photon that we get. Anything past that is ultraviolet. That's why this 7 to 2 is showed with a dotted line here, and it's kind of grayed out. That's because we can't see that one. That's actually too energetic for us to be able to see. That's in the ultraviolet spectrum. And we can see that it's called the Balmer series. The Lyman series, that's the first series labeled here, is any time we go to n is equal to 1. All of these transitions would be ultraviolet, because notice the gaps in all of these energies, 2 to 1, 3 to 1, 4 to 1, 5 to 1, all of these are more energetic than the visible ones. Likewise, the Passion series, we can see those all end at n is equal to 3. These would be infrared, because all of these transitions would be less energetic than the ones in the Balmer series. One thing to note here as well is that this scale here is not, or this energy level diagram is not drawn to scale. As you're looking at this, you might be thinking, well, why aren't some of these Passion series, why aren't some of these visible? Because those seem to have about the same length as some of these transitions here, the same amount of energy. Well, in all reality, these get even closer and closer together as we work our way up. So that's why it might appear that way, but it's not really the case. Alright, so we've explained how atomic emission spectra are produced. What we want to be able to do now is we want to be able to rank photon emissions and absorptions in the Bohr atom by wavelength, frequency, and energy. So here's what these sorts of questions might look like. Just a couple of questions here that I've labeled lecture problem number 7. First question, which transition in the Bohr atom will emit a photon of the longest wavelength? So, a couple things to point out here. We're just given some options. Where our options are n is equal to 2 to 1, n is equal to 1 to 2, n is equal to 3 to 2, n is equal to 2 to 3. The fact that we were asked about which transition will emit a photon can narrow down our choices. If we are emitting a photon, that means we're giving off energy. So the atom has to be going from a higher energy state to a lower energy state. So we can get rid of any of the options where it's going up. So we can eliminate option B and option D, because there the atom is going from a lower energy state to a higher energy state. So we know the answer has to be either A or C. So we're asked which one will emit a photon of the longest wavelength. Longest wavelength, that's going to mean lowest amount of energy. The longer the wavelength, the lower amount of energy. So think about which gap in energy, is it 2 to 1 or is it 3 to 2, would have the smallest energy gap. Well, that would be C, 3 to 2, because we know as we get higher up in energy, those energy levels get closer together. That is the key there. So the answer to number 1 is C. Alright, question number 2. Which transition in the Bohr atom will emit a photon of the greatest frequency? Again, we are emitting a photon, so we can only deal with transitions where the energy state decreases. And it just so happens in these, all of these are getting smaller, so all of these are still in play. Greatest frequency, that would be the greatest energy. So 4 to 1, 5 to 2, 6 to 3, 100 to 7. Notice these first three are all the same number difference. They're all a difference of 3. However, 4 to 1 would be the greatest energy gap, because we know the lower we are on the scale, the bigger the gap is between the energy levels. So A would be the biggest energy gap amongst the first 3. The confusion might come from this last one. Is 100 to 7, is that energy gap bigger than 4 to 1? Well, the answer to that is simply no, it's not. If we haven't shown it yet, we will show it in class eventually. We'll try to draw this energy diagram to scale so we can see why 4 to 1 would be a bigger gap than 100 to 7. So the answer to number 2 is actually A. It is 4 to 1, and that would be the greatest frequency being emitted. Alright, so we have finished the learning targets here for this video. I know that was a lot of information right from the start there from the video. We will summarize all this in class, and I'll be asking you some different questions to help you gauge your learning and understanding of what we saw here.